In this section, let's start to try to understand the rates of reactions. So, what is a reaction rate? When I talk about a reaction rate, what I'm referring to is the time it takes for reactant A to convert to product B. Okay, so a certain amount of time will pass for the reaction to happen. Some reactions are really fast, some reactions are really slow. Other reactions are kind of in the middle there. So here I have a couple of different examples of reactions. And so on the left-hand side, we've got a reaction with a fast rate. We have A and B, they're going to C, okay? At 16 minutes, I have quite a bit of C and about half of A and B left. Now, on the other hand, I've got one on the right side with a slow rate. I've got X and Y that are converting to Z. Well, at the beginning of the reaction, I have all reactants. But after 16 minutes, the same time that passed for reaction A, well, I still have mostly X and Y and not a whole lot of Z has been created. So this reaction has a slow rate. When we look at reactions, there's different things that are happening because for a reaction to occur, I have to have molecules that will interact with each other, okay? A reaction can't occur if I have one reactant all the way over here and the other reactant all the way, over there. They have to be close to each other, and then they have to collide with each other because I have to have bonds from my reactants break and new bonds making my products form. And so we can posit some transition states where as a reaction is going, when stuff collides, at that moment, we're starting to break some bonds and forming some others. And so there's an amount of energy that occurs there. Breaking bonds takes energy. Forming bonds typically gives us energy back. And so at the point of collision, I'm breaking those bonds, so that's costing energy. And then I'm forming new bonds, which is giving me energy back. Okay. And so we can get exothermic reactions where my products are going to be at a lower energy than my reactants. So I've given off energy. Okay. So in this case, energy is a product. Okay. I have endothermic reactions where now I have to intake a bunch of energy in order to get the reaction to go. For these, energy is a reactant. Okay. And so these are going to cause different rates of reaction as well. So for my reaction to occur, I have to have a collision. All right, again, if I have something all the way over here and something all the way over there, I can't form any products because they're not interacting with each other. They have to smash into each other and collide for that reaction to get started. The other thing is things have to be done in the proper orientation. All right, if I need to break one bond and I need to form a specific new bond, if the wrong two things smash into each other, that new bond is not going to form and my reaction's not going to happen. And that collision needs to give enough energy for that activation energy. So that activation energy is the amount of energy it takes to get that reaction to go. So I need enough energy for that. Okay, so we can look at this in terms of what is called collision theory. All right, and so in this case, you can see, I've got two different pathways there. All right, I'm trying to make a target product. My target is that. All right, my target is this one. There we go. All right, so my target is that oxygen and nitrogen stay bonded together, but the chlorine molecule, I'm going to break that chlorine-chlorine bond and form a new bond between the nitrogen and the chlorine. So if I collide in the orientation that has the chlorine smashing into the nitrogen where I want the new bond to form, then the reaction could potentially occur as long as we were at or above the activation energy. But if I'm oriented a different way, if my nitrogen and oxygen, my nitrogen monoxide comes in and the oxygen bumps that chlorine, well, they're just going to bump off each other. Okay, Okay, it's not going to happen because the wrong things collided. So let's take a look here. Okay, so I have nitrogen monoxide and nitrogen trioxide. They're going to collide and make two nitrogen dioxides. So what needs to happen is the nitrogen from the nitrogen monoxide needs to collide properly with an oxygen from from the nitrogen trioxide. Okay, because I need to break a nitrogen oxygen bond from the nitrogen trioxide, and I need to form a nitrogen oxygen bond off the nitrogen monoxide. Okay, so what can happen here? So if two things are coming in to collide, even if they are in the right orientation, it can still be an ineffective collision if it's not at or above the activation energy. So in this situation, I do have that nitrogen that's in blue coming in to collide with that oxygen on that nitrogen trioxide. This one's ineffective because even though the right two things are going to bump into each other, they're not at the right energy. Okay? This one's ineffective because here I have the oxygen for the nitrogen monoxide colliding with the nitrogen from the nitrogen trioxide. That's not the type of product we're trying to make. This one's ineffective because I have two oxygens bumping into each other. That's definitely not the reaction that we're going for. But this one is also still ineffective because I still have the wrong things colliding. Nitrogen and nitrogen are bumping into each other. Not what I'm looking for. However, this last one, now I have the right things bumping into each other, as well as being at the right activation energy. So I've met the condition of things colliding. I've met the condition of things colliding in the right orientation. And I've met the condition of being at or above the activation energy. Okay, so this one, 3 conditions met. Okay, first condition again, we collided. Okay. 2, the right things collided. So I was in the correct orientation. And lastly, I was at or above the E sub A, the activation energy. Okay, so those things have to be met in order for a reaction to occur. We can express the reaction rate by understanding that what's happening is the concentration is changing per unit time. So I'm losing my reactants, I'm gaining my products, and so I'm going to deplete my reactant and I'll gain my product. So I can show this as a negative change in concentration of A over the change in time, or I can show it as a positive change in the concentration of B over time, because I should be gaining B. So the concentration of B will go up, because that's the product. The concentration of A will go down, because that's the reactant. So we have to have all these conditions met in order to get a reaction to go. So a lot of factors influence that rate. And so it's a lot more complicated than just I pour A, I pour B, boom, we get a product. A lot of little things are going on behind the scenes there.